Okay, let's get started. Looks like we had a lot of margin in the break, so next break we'll have less margin. Okay, so this is where we left off, basically. We're talking about hybrid memory systems, and we're going to cover some issues. We're not going to be able to cover a lot of these issues. Basically, some of them are, if you have DRAM versus PCM, let's make it concrete, both of them in your system. Do you use DRAM as a cache, or do you use DRAM as another part of main memory? That's one question, right? What is the granularity of data movement, data management? Is it fine? Is it coarse? How do you handle it? Who manages it? Hardware, software? Is it hardware, software cooperative? There are downsides and upsides to both. Software is usually very slow, as you know, but some things, it has a lot of scope also. When do you migrate the data? How do you design a scalable and efficient large cache, assuming if you want to manage as a cache? And there are a bunch of other questions over here. Actually, we laid it out when we wrote some papers in the past. But let's take a look at some options. I think I'll look at the option of DRAM as a cache for phase change memory. In this case, phase change memory is main memory, and DRAM caches memory rows or blocks. And the benefits is you get reduced latency on a DRAM cache hit, and you can actually use DRAM as a cache that filters your writes. Basically, you can accumulate your writes into DRAM before you write back into the phase change memory. Right? So that gets rid of a lot of the writes into the phase change memory. It's a big write buffer. And the memory controller hardware manages the DRAM cache. This eliminates the system software overhead. Actually, system software has a lot of management overhead in terms of caches that people are trying to remove. We're going to get back to that later on. So there are three issues, at least three issues in the design of this DRAM cache we're going to cover. Basically, what data should be placed in DRAM versus kept in PCM? What is the granularity of data movement? And how do you design a low-cost hardware-managed DRAM cache? If your DRAM is, I don't know, 4 gigabytes still, that's a very large cache to manage in hardware, right? How do you design this cache? Is it going to be similar to the caches that we have on chip, which are much smaller today, maybe 32 megabytes? There are two idea directions. We're going to cover some of these. One is locality-aware data placement. I'm going to give you the basic ideas and some results, and cheap tag scores and stores and dynamic granularity. But before that, I think this is a paper that I'm going to mention. This is concurrent with the work that we've done. It looks at a system-level perspective. Basically, the goal is to achieve the best of both DRAM and phase change memory and NVM. That's the idea of a DRAM cache. Well, that's the idea of hybrid memory systems. If you want to use DRAM as a cache for PCM, you want to do that because you want to tolerate the latency of PCM, and you also want to tolerate the write bandwidth and the endurance issues that we've discussed. And we want to minimize the amount of DRAM that we have in the system without sacrificing performance and endurance. And we're going to use the PCM as main memory to provide large capacity at good cost and power. So basically, the system looks like this. This is depicted in this paper by Moin Qureshi. Yes? Yes. Yes, that's right. I agree. This is not, we haven't talked about non-volatile part. Even in the paper that I mentioned earlier, actually, we didn't even take advantage of non-volatility at all. But yeah, if you want to use this as persistent memory, meaning whatever you write, you want it to be persistent, now it's buffered in DRAM, and you have an issue in terms of consistency, right? Exactly, that's what I was going to say. That's another possibility, right? So yeah, you could add a battery to drain. Of course, that depends on the size of this DRAM and also the capacity of your battery. Now you get into some trade-offs, right? Yeah. Yeah, but we're not even exploiting the non-volatility at this point. Okay, so basically, this is the idea over here. You have DRAM buffer. It buffers maybe reads and writes, and then there's a write queue into the PCM. How do you design that DRAM buffer? This paper talks about some write filtering techniques. Basically, you have pages from disk that come and that get installed only into the DRAM, not PCM. That's one idea that's in this paper that says, okay, you don't want to write into the PCM, and this makes sense, right? You do partial writes like we've discussed. Only dirty lines from DRAM page are written back to phase change memory. That makes sense. And maybe you can do a page bypass Basically, you don't want to, as I said earlier, the principles in this paper are actually similar to the principles that we have. You don't want to write into this memory, and you want to minimize the reads from this memory somehow, except the design over here is a little bit different, as you can see. You don't want to write into it. Whenever you just have a page over here that you're evicting, maybe you don't write it back to phase change memory. Maybe you have a reuse predictor that says, we're not going to reuse it, so don't put it back into phase change memory. That way you get rid of writes into phase change memory. Okay, so this paper did something different in its evaluation. So it looked at a more system-level evaluation. It didn't really assume that we assumed the worst case, basically, in our evaluation for PCM. We said the capacity is the same. This paper said, okay, phase change memory capacity will be much larger than DRAM. So what they simulated was several different systems. So this is a system with 8 gigabytes of DRAM. And they said the cost of this system is going to be similar to a system with 32 gigabytes of PCM. That's the this is the normalized execution time of a bunch of workloads over here. And this is the geometric mean. And they modeled the page faults over here in some way, in a probabilistic way, actually. As you can see over here, they assumed some hit rates. I still hear this noise. I don't know why. I thought I got rid of it. Oh, is it?
1-1.
Oh, okay. Okay, yeah, somehow. Yeah, that's a little switch. Maybe, yeah. Okay, is this better? Okay, good. Okay, maybe the noise was dominating. That's why I was hearing only noise. So that's now it's better. Signal to noise ratio is much better now. Okay, so basically, this is the assumption. And DRAM block size is the same as PCM page size, and you can see the latencies over here. So what happens if you replace 8 gigabytes DRAM with 32 gigabytes PCM? Basically, as expected, you gain higher performance, right? Oh, it's kind of obvious. Even though the PCM latency is longer, because you have much higher capacity, now you get rid of some page faults. As a result, the performance is much higher. But the more interesting comparison from my perspective is this one over here, 32 gigabyte PCM and 32 gigabyte DRAM. As you can see over here, there's a big performance gain because of DRAM. So DRAM is still higher performance. And the way this paper tried to overcome that performance loss is by having some amount of DRAM in the system and some amount of PCM. So 1 gigabyte DRAM plus 32 gigabyte PCM. And if you actually have that, and if you use the techniques that we just discussed in the previous slides, you get very close to the 32 gigabyte DRAM system. So you can see that overall performance gain is, or overall performance loss compared to 32 gigabyte system is very slight over here, a few percent. So that's the idea. A hybrid memory technology gets you closer to a fully DRAM technology with very small amount of DRAM. As opposed to 32 gigabyte DRAM, you have 1 gigabyte DRAM, and you have 32 gigabyte PCM. So you could argue that you have 32 gigabytes overall, and you're gaining, and that's true also. But, well, maybe the better comparison would be with 31 gigabyte PCM, but that's okay. So that's the idea of the hybrid memory system. And I think this is a system-level perspective, which is really good to show. If it's really true that phase change memory is going to be much more dense at the same cost, you gain a lot of performance compared to the same cost DRAM. Okay, so this paper also showed that basically the key takeaway is phase change memory DRAM hybrid performs similarly to similar sized DRAM. You get significant energy savings also. The energy is over here with the PCM DRAM hybrid. So this is 8 gigabyte DRAM, this is hybrid, and this is 32 gigabyte DRAM. So the hybrid PCM DRAM is actually much more energy efficient, as you can see over here. And they also look at energy delay product and power. So DRAM power, 32 gigabyte DRAM power is much higher, as you can see over here. And the paper also looked at lifetime, similar to what we did, and average lifetime is about 9.7 years in that case. And there's still no guarantees. So it was a bit more optimistic, as you can see, in terms of its evaluation. Well, we were a little bit more pessimistic in our evaluation. Yes? You mean in this case? Well, I don't remember this paper's assumption, but I believe they modeled something like this. Yeah. But you can read the paper for more detail. This is published in the same conference. So at the same conference, there were 3 papers that looked at new technologies, specifically PCM. OK. So this is the paper. You can take a look at it. OK, so I think this data placement, this paper tackled a little bit, but there's more work to be done in the data placement in hybrid memory. How do you actually place data? And this is a general problem, actually. It's not just DRAM, PCM, but you can have memory A and memory B. And at least this is fast and small, and this is large and slow. It looks like caching, right? So what do you decide to put where? So there's a migration overhead, clearly. And which memory do we place each page in to maximize system performance? So there's also if you actually place too many pages in over here, then you're actually leaving this imbalanced, right? So you have this channel. If there are 2 different channels over here, if you're serving almost always from this channel, then this channel is idle, and you have a problem because you're not utilizing your channel bandwidth really well. And this is actually expensive. Having a channel is expensive. So it's not as easy, I think. And page migrations have performance and energy overhead. So I'm going to give you a couple of ideas. This is something that we have looked at. Basically, if you can characterize your access patterns and guide data placement in hybrid memory, you can do better. The realization is that if you're doing streaming from memory, you can actually do it as fast in PCM as in DRAM. Because usually memories work by buffering things inside a row buffer, let's say. And you're streaming through that row buffer. And you're prefetching internally also. You can design your memories to prefetch internally as well. So streaming accesses are easier to handle in cheap technology, similar to expensive technology. So if you're streaming, it's better to put that data in PCM. Actually, if all you're doing is streaming, maybe you need just buffering and a tape far away, right? And you don't care about the initial latency, of course. And then you stream from the tape and all the way into your system. And you're very low cost effective, right? But of course, streaming is not the only thing we do in life. There are random accesses. And expensive technology is usually good at random accesses, random access much faster in DRAM. So the idea is very simple once you realize that. Place data that you're accessing in a random access manner with some reuse inside DRAM, and streaming data inside PCM. And that's the idea. If you don't have any reuse on data, basically, you bring it to some fast buffer, and then you don't put it back into any part of your cache hierarchy. I think that's the fundamental caching principle. But this is random access data with some reuse. For example, you're accessing some row, and you want to keep it in DRAM because you're going to access that row again. Right? OK, that's the key observation. So the key observation is that row buffers exist in both DRAM and PCM. Row hit latency is similar in DRAM and PCM. Actually, you can architect the memory to ensure that row hit latency is similar, because row buffers are actually not, as we know, it's not DRAM technology, it's not PCM technology, it's more like SRAM, right? And row miss latency is small in DRAM because you access the DRAM cells, and it's large in PCM because you access the PCM cells. So the key idea is to place data in DRAM that has 2 properties. That is likely to miss in the row buffer, that has low row buffer locality, because miss penalty is smaller in DRAM, and that is reused many times. Basically, cache only the data that's worth the movement cost and DRAM space.
If you replace DRAM with cache, SRAM,
Mm-hmm.
and the other one with DRAM, you decide to do it, read the same.
That's true, yes. It's a cache, exactly, it's a caching optimization. But I think the...
No, here it's not. This is not the cache here.
In DRAM, it's still the cache here, yes. It's still the cache, yes. Yes, but I think the difference is SRAM is on chip and DRAM is off chip, so this trade-off doesn't exist, right?
No, I would say the concept is very similar.
Yeah, that's true. But SRAM, the same level of trade-off doesn't exist with SRAM today because it's on chip, right? If SRAM was off chip, I agree, for sure. But since SRAM is on chip, you don't really care about the row buffers and all that locality.
Just make sure in this configuration
It's a cache, yes. It's a cache to...
So everything is still in the PCM, you just...
you don't always cache in DRAM, though.
Yeah.
Basically, this is the decision of caching. Yeah, this is the caching decision. I mean, I fundamentally agree, yes. But the fact that SRAM is so fast in everything breaks that a bit. Okay, so what... these are, again, our pessimistic results, not very optimistic. Basically, we look at 16 gigabyte PCM, 16 gigabyte DRAM, and this is the dynamic optimization that I just discussed, where to place. And it gets you basically somewhere in between. You get significantly better performance than all PCM, and you're still not close enough to DRAM with this sort of caching mechanism. If you had 16 gigabyte DRAM, you would do better, basically. But it's somewhere in between, and we look at other metrics also. So I think there's a lot more to do in hybrid memory area. So we've actually been looking at some other things. Usually, existing solutions are heuristics that consider only limited part of memory access behavior. And as you add more information to the memory access behavior, you can do better. And I'll give you some ideas. I think there's more to be done in this area. So one of the things that we wanted to do was to have a model that actually predicts the performance impact of different data placement decisions. And this model needs to take into account multiple things, but we also found out that it needs to take into account memory level parallelism, the number of concurrent memory accesses from the same application when a page is accessed. And this affects how much page migration actually helps performance. So I'm going to show this pictorially. So let's assume that you have request to page 1. That's a memory request. And after you migrate, you basically reduce the access latency to that page because you migrate into a faster technology, right? So migrating one page reduces stall time by T over here. Now let's take a look at a case where you have 2 requests concurrently to page 2 and page 3 over here from the same process, from the same core, let's say. If you migrate only one of those pages, memory A, memory B means this is one type of memory, slow memory, and this is fast memory. If page 2 and page 3 are requested by the same application and they're both in slow memory, the application will stall by some amount of time. If you migrate only one of those pages that the application demands to the fast memory, you don't gain anything because the application still is waiting for the page that it requests concurrently with this page from the fast memory, slow memory, because you didn't migrate that one. So in order to be able to reduce the application's stall time, you really need to migrate both pages. And that's the idea over here. I think this is classic memory level parallelism. If you've studied the topic, you will know. The downside is now you have a caching choice, right? If an application needs only one page over here, you gain a lot more over here given the same amount of space in the cache. Right? So you would like to ideally migrate things that would buy you the highest utility in terms of performance. And that's the idea. Page migration decisions somehow need to consider multiple metrics. And we found out that this is actually one of the important metrics. Robot for locality is another important metric that we discussed. So our goal in this paper was to have a generalized mechanism that directly estimates the performance benefit of migrating a page between any 2 types of memory and places only the performance critical data in the fast memory. And I'm not going to go into all of the details, but we call this the utility-based hybrid memory management. And we looked at different types of memory in this case. The key idea is for each page, use different characteristics to calculate an estimated utility of migrating the page from one memory to the other, assuming 2 different types of memories. Utility means performance impact, how much performance you will gain, how much you will reduce the stall time of an application, basically. Assuming you do that well, you migrate only pages with the highest utility, pages that improve system performance the most when you migrate them. And this is a complex equation. It's not as simple. So this is how we estimate the utility. This is the part that I'm going to discuss. And once you estimate the utility, you migrate only pages whose utility exceed the migration threshold from slow memory to fast memory. So you need a threshold. And you periodically adjust the migration threshold because that changes in the workload also. So what are the things that we take into account? The application stall time reduction. How much would migrating a page benefit the performance of the application that the page belongs to? That takes into account robot for locality and memory level parallelism. And also application performance sensitivity. How much does the improvement of a single application's performance increase the overall system performance? So if you may be running multiple applications, how do you decide which application's page to migrate? Right? I think that's a harder decision to make also. Assuming that all the applications are equal, you need to have a performance metric, and you're optimizing that. If all applications are not equal, of course, then maybe you prioritize some applications, right? So basically, this is the utility metric. We have an estimation of the delta stall time reduction that you would have if you migrated this particular page that the application is trying to access times the sensitivity of the system performance to this application's performance at that point in time. And the paper goes into more detail as to how you would estimate each of these, but we don't have time to do that really. If you're interested, you can. But the key idea is basically to consider the utility of a migration decision somehow in a comprehensive manner. I'm not claiming that this is the most comprehensive thing, but this is the most comprehensive thing that I've seen so far. But I'm sure there are other things that can be taken into account. So what are the benefits? Basically, this is the performance improvement in terms of weighted speed up, system performance. This is what happens if you migrate all pages. Whenever you access PCM, you migrated the page into DRAM. This is frequency-based migration. Basically, you have a frequency-based mechanism that decides, oh, these are the frequently used pages, and you migrate them. So this buys you actually a lot, as you can see. And these are workload memory intensity, how intensive is your workload. And this is robo for locality aware mechanism that I just discussed. So that buys you a little bit more. And this is if you use utility. So utility-based mechanism is slightly better. Of course, if the workload is very memory intensive, you become even better because you need to be more judicious in your decisions of migration. And that's the idea. As far as I know, this is the state-of-the-art mechanism right now. And this is actually relatively general. We look at different access latencies of the slow memory as a multiplier of the fast memory. So this is, for example, the slow memory is really slow over here. Here, the slow memory is slow, but not as slow as here. Here, the slow memory is 3x slow, for example. Here, the slow memory is 7.5x slow. And in terms of writes, it's about 20x slower compared to fast memory. And you can see that as memory becomes slower, the performance reduces as expected. That's what you would like to see. But the performance improvement of utility-based management actually increases in a relative manner somewhat compared to this part over here. I think it's good to try to develop more general techniques, but there's complexity associated with these models also. So I like the research in this area. Okay, any questions? There's actually a lot more research that I'm not covering. This is the paper that I just described. I think the big challenge is enabling an emerging technology to augment DRAM in this case. That's what we're looking at. We got rid of replacing DRAM. Now we're trying to augment DRAM, which means that you need to somehow manage hybrid memories. And another challenge is designing effective large DRAM caches. So let's switch gears. We've talked about this as a DRAM as a cache, right? So how do you design these DRAM caches is something that has fascinated some people over the last decade or so. So I'm going to talk about some ideas over here. So one problem with a large DRAM cache is if your DRAM cache is 4 gigabytes, it requires large metadata. How do you actually reduce that metadata? Where do you put that metadata? So if your DRAM cache is, let's say, 4 gigabytes, and if you're storing information at the granularity of 64 bytes, that's a lot of blocks that you have in that cache, right? I think 4 gigabytes is 2 to the 32. 64 bytes 2 to the 6, so you have 2 to the 26 blocks. It's hard to imagine a memory controller that stores that entire cache tag store. So where do you put that? So when you get a load X, you need to consult some metadata, and the metadata should tell you it's in DRAM or it's in PCM, right? If it's not in DRAM, you assume that it's in PCM. And if it's in DRAM, you access it. If it's not in DRAM, you access something else. So this metadata storage is actually very large. First of all, if you actually have a huge metadata store, that's energy inefficient here, but it also has a scalability problem that we discussed with the Bloom, with the refresh earlier, right? If you actually increase the size of your memory, if you increase the size of your DRAM for whatever reason, now you cannot adapt to it. You have to provision for the worst case size that you can put into your DIMM slot. So there are several ideas that I'm going to go over. One idea is you store the tags in the same row as data in DRAM. Basically, the DRAM itself is not only a data store, but also a tag store. And in this work, we said that you should store them together, the tags and data in the same row. Another option is, of course, you store the tags in one part of DRAM and the data in some other part of DRAM, and that doesn't perform well, as we will show in the results. If you actually do them together, that's good because you can access data and metadata together, and you can do the tag check quickly, and you can, if the tag check matches, the cache block is in the same row, which you've already opened, hopefully. Okay, so the big benefit of this is there's no need for tag storage on chip, right? You have the tag storage inside the DRAM completely. But in order to be able to check whether some cache block, the data exists in DRAM, you need to access DRAM. So it costs you a DRAM access regardless. Cache it is determined only after DRAM access. And a cache it actually requires 2 DRAM accesses. The first one is to check the tag. And if the tag matches, you access the data. The hope is that the second access is a row buffer hit because you're storing data in the same row, data and the tags in the same row. So that's the first idea. The second idea is, yes?
Explain what the tags are meant for?
Oh, tags are meant for determining whether the cache block that you're looking for exists in DRAM. So basically, this is what you're trying to do. Basically, you have an address X. You want to somehow figure out, is X in DRAM or not? So how do you figure that out? You need to consult a tag store or metadata store. And the purpose of those tags is to say, oh, these are the things that I store in this row in DRAM. Make sense? It's like a cache, basically. Same as a cache.
So I think you may miss to say that the row depends on several bits from the address that will get you to the row.
Oh, that's right, yes. So I assume that
So
was...
you are going just to one row, not trying to...
Exactly, yes. Basically, based on the address, you go to a row, and that row gives you the tags, and you match the tags. If it doesn't match, then you know that the data is not there. Yes?
Once you open the row, you can check the tag and read the data parallelly. You don't have to wait to the validation of the tag.
That's right. You can speculatively pipeline, basically. I mean, you cannot do it completely in parallel because you're reading from the row, but you can pipeline. I mean, you can even have a predictor, right? Which cache block you're reading. It depends on the associativity also, right? If this is one-way associative, then you just look at one tag, probably direct map, basically. But yes, that's right. Okay. Okay. So the big downside over here is cache it is determined only after a DRAM access. So can we actually get rid of that DRAM access in the common case for just tag check? And the idea is very simple. As opposed to storing all metadata in DRAM, we still store all metadata in DRAM, but we cache some of it in on-chip SRAM. So basically, now you're caching the metadata. It's actually a relatively old idea. People have proposed caching tags to reduce access latency of the tag store in the past, even on chip, in an on-chip context. But in this case, the reason we are storing all metadata in DRAM is metadata is large, but the good thing is this cache of the metadata can be small. Okay. I mean, this is the management overhead that we were discussing, right? We keep adding more management overhead into the systems, and that's how it is. Exactly. It's caching. Yeah. Basically, it's a tag cache. You cache only a small amount to keep SRAM size small. And if you have good locality in your tag accesses, that's great, right? Actually, we see that you get at least 80% hit rate in this small cache in the paper that I'm going to talk about. Okay, so that's the idea, basically. You can keep this very small. There's another idea that in this work that I'm going to show the evaluations of. You can actually, what is the granularity of transfer of data? Some applications actually benefit from caching more data in a single cache block because they have good spatial locality. This is obvious. Others do not. It's a huge waste to have a large block because you're really wasting cache space. You also waste bandwidth, actually bandwidth moving from PCM to DRAM. So the idea was to have a dynamic caching granularity policy, and we used a cost-benefit analysis to determine the best DRAM cache block size for a given application. And we used what's called set sampling. And the idea is to group memory rows into sets of rows. Different sampled row sets follow different fixed caching granularities. Some of them follow 64 bytes. Some of them follow 256 byte granularity. Some of them follow 1 kilobyte. Some of them follow 4 kilobytes, let's say. And you basically check which one buys you a better hit rate. In this case, it was a better stall time, but let's not go into that. You can read the paper. And the rest of main memory follows the best granularity. So if you somehow figure out, based on this dynamic profiling, the best size at that point in time is 1 kilobyte, you follow 1 kilobytes. Right? And then you can change that over time. There's overhead and changing, of course, that we're not going to go into. And there's a cost-benefit analysis. You basically look at access latency versus number of cachings, and you can see that, and it's performed every quantum, like time quantum. So if you do this, it actually buys you a benefit. It's additional complexity, of course. But we're basically trying to solve the fundamental problem that a single fixed cache block size is not good enough.
You try to make it further to stride prediction in non-contiguous caches?
Yeah, that's we don't. Yeah, I mean, you can certainly. There's no end to this, right? Sure. There's absolutely no end to this. You could actually optimize it, but you wanted to stop at the newest of the ideas. Okay, so let's take a look at the performance benefit. Actually, this is not a fully fair comparison. So this is what happens. This is the paper. You can take a look at it. But this is basically the performance of all of the tags are in your SRAM in the memory controller. That's a huge tag store, basically. And the parameters are in the paper. I don't remember right now, actually. It's been a long time. And this is the overall performance loss that we have compared to that. We call this the timber. Tim means tags in memory. And I don't remember what timber stands for, but timber sounds good. But basically, you lose about 6% performance compared to having all your tags in the tag store. It's not a fair comparison because this SRAM can also benefit from this dynamic caching granularity. And it's somewhere in an extended version of the paper that I didn't put over here. So actually, you can do better than if you have SRAM dynamic, you could do better. So basically, let's take a look at what are these different things. So this is tag store inside the memory controller, huge tag store. Not good for energy, but good for performance. You can quickly decide whether the data is in DRAM or PCM. This is region-based. You have some region in DRAM that's dedicated to the tag store, and the rest is data. They're not in the same row. If you do that, your performance actually halves over here because you're doing 2 DRAM accesses every time you get a hit, and they're going to 2 different rows in DRAM. So that's not good. If you actually put the tag and the data in the same row, at least you exploit row buffer locality, so that buys you about 20% over here. I mean, 20% in this relative scale, not 20% compared to this. So it's not bad. It's still 30% lower than SRAM tags. In this case, you have DRAM tags, and tags and data are in the same row. We don't cache those tags. If you cache the tags, that gets you to around 88% or so, I think. Basically, you lose about 12% compared to having the entire tag store inside the memory controller in SRAM. And on top of that, if you do this dynamic caching granularity, which is a bit more complex, then you get a little bit more. That's the idea. Okay? I think there's a lot more to optimize, as you mentioned. You could do prefetching. Actually, we were looking into, for example, this tag cache. You could prefetch into that also, right? You could prefetch the tags if you're actually going through memory. And that would improve your hit rate significantly over here. Yes?
Do you remember if in this comparison you actually used some of the on-chip cache in order to cache the tags, or is it additional?
Yeah, this is additional. But that may or may not be a good idea depending on where your on-chip cache sits, actually. You could potentially do that. This is completely additional. It's a small amount of SRAM that we had over here. I believe it was 8 kilobytes or so. Whereas here you needed, if I remember correctly, 8 megabytes or so.
Okay, but if you would not use the on-chip cache, I would expect performance to drop significantly regardless of what you did here.
I see, because you're taking away from your on-chip cache. That's the
use metadata here.
yeah. Yeah, I mean, that's one of the reasons why we didn't want to use on-chip cache. It's also the placement of the on-chip cache, right? It's in the we want to do this in the memory controller. But you could potentially do it in the on-chip cache before you miss. You check it, right? That's also possible, I think. Actually, you don't have to do this in the memory control. I take it back. Because your request may be coming from the on-chip cache miss, right? You could actually check that.
Just to make sure, it's not an idea. We just expect it to be lower.
Because you're using the cache space. Yeah. Yeah, I think it's 8 kilobytes. It depends on how much you lose based on that 8 kilobytes. I mean, there's a lot of other work that we've done and that others have done also that show that a lot of the data in your on-chip cache are dead anyway. So maybe, yes?
Is there an estimation of the power cost or energy cost of just accessing both eagerly?
Oh, DRAM and PCM? Well, I don't have that estimation, but I expect that to be bad all the time if you do that. Maybe that doesn't satisfy you because I didn't give you a number, but but I expect that to be bad because that also wastes your bandwidth, right?
Because if what I'm trying to increase is performance,
Mm.
perhaps I could.
Yeah, maybe if all you care about is performance, maybe you do that, sure. But I think, yeah, power cost may be high.
And
Because PCM accesses are actually energy hungry.
well, could they be less hungry if it were to know to be aware of what the DRAM has in it? So perhaps I could just produce some kind of protocol that it says, okay, I know I don't have it, so you probably just go to the DRAM and get it from there. I will not process your request for that.
I see. Yeah, I mean, then you're building some sort of tag store or predictor, right? So you need to have a mechanism.
Inclusive or exclusive? I think that's, well, do you know whether it's exclusive or inclusive? Whether all information in DRAM is also,
In this case, I think we assumed inclusivity.
okay.
Yes. But I mean, if you have an exclusive cache, then that's a different decision, of course. But that's another decision, yes.
Why it's matter for your question?
Because if the PCM doesn't have the data, it cannot process the request. It would be much easier logic to just say, okay, I'm not going to
No,
process.
even if it's inclusive, it can have something say that.
That's true.
It's in the other side, so don't bother. Or
That's
something
true,
like
yes.
that.
But I think regardless, you need to have some sort of tag store or prediction mechanism.
I think
Yeah.
going to the PCM, which is much bigger, you sort of lost the gain that you want to get out
Yes.
of it, just by accessing it. And you have to read it, to read the text to know that it's not there.
Yeah. Okay. Okay, let's keep going. I think I've covered all of this. And this is the energy efficiency. This is if you have an SRAM tag store. If you're region-based, you lose energy efficiency. This is in terms of performance per watt. And this is if you have tags in memory. This is if you cache the tags. And this is if you have dynamic granularity. Actually, dynamic granularity helps energy efficiency significantly because that reduces your data movement a lot. As opposed to moving always 4 kilobyte blocks, you move sometimes 64 bytes, sometimes 256 bytes, sometimes 4 kilobytes, right? Depending on your locality. Okay, so this is the paper that I mentioned. There's a lot more work done in this area. I'm not covering all of that. I think there are still DRAM caching papers that appear once in a while. Personally, I think I'm not a big fan of working in this area, but there are sometimes ideas that students want to work on. So this is one recent paper that we have done, where you looked at, actually this is collaborative with Intel, where we looked at different types of DRAM caches, and there are many recent options. If you're really interested in it, I'm going to point you to these papers. So basically, these are different caches that have different types of approaches to how you handle the DRAM cache hit, DRAM cache miss, what is the replacement traffic, what is the replacement decision, who manages the replacement decision, does it support large page caching, So there's a lot here that I'm really not going to cover. So this gives you the complexity of the space, if you will. So for example, some of them make the replacement decision in a hardware managed base. Some of them make the decision in software managed base. What else? These are the traffic that they assume in package, latencies that they assume, and what kind of coherence that they provide, TLB coherence. If you're interested, you can read this paper. This is also one of the state-of-the-art works. This was published in Micro last year, in 2017.
So green is good, sort of?
Green is, yeah, that's according to our evaluation, that's supposed to be good. Red is supposed to be bad, basically. But you can take a look at it and make your own decision.
Orange is the best. Okay.
Yeah, of course. I mean, that's the proposal, right? It's supposed to be all green. Okay, so I'll give you the basic idea over here. So this is a hardware-software cooperative solution, basically. It's not purely hardware. It's not purely software. Some of these are purely software over here. Some of these are purely hardware. I've discussed some of the purely hardware solutions. But this is actually a hardware-software cooperative solution. Basically, what we do is, and I'm not going to give you all the details. You can read the paper for more detail. The work tracks presence in the cache using TLB and the page table. There's no tag store needed for the DRAM cache. The problem is, if something changes, you need to change the TLB, right? If mapping changes, you need to change the TLB. So there's an intelligent address mapping mechanism that you have between phase change memory and DRAM, or hybrid memory, if you will. And we have a TLB coherence protocol managed by the memory controller to be able to shoot down the TLBs. Okay, if you don't understand that, read the paper. And there's another contribution, which is the bandwidth-aware frequency-based replacement policy. It basically tries to save bandwidth. And if you look over here, this is the DRAM cache latency, and this is the speed up that you get. And this is the DRAM cache bandwidth compared to the baseline, compared to the slower memory technology. So we're assuming cache latency is actually similar to the other technology, but cache bandwidth is much higher. And you can see that the performance improvement of this caching mechanism is relatively higher. But I think to be able to fully appreciate it, you really need to understand all of the other mechanisms that were proposed in the past. And we really don't have time to cover all of those different caching mechanisms. But this is, as far as I know, this is the state of the art in DRAM caching. But if you don't understand anything, don't worry about it. But if you're interested in working in this area, certainly there's a lot more to do. I'm not sure how big of a step it will be compared to what's already been done. But what's missing, in my opinion, is something that's really fully practical that can really go into products. I'll leave it there. Any questions? I went through this really fast, I understand. But if you go into DRAM caching, it'll take us for some time. And personally, I find this a little bit less interesting compared to other topics. So computer architects are very good at, I think, converting every problem into a caching problem. The ISCA conference, International Symposium on Cache Architecture. It's been caching for a while. And as I prepared you in these lectures, I wanted to start with a different mindset, right? And then we went back to caching. Although locality principle is very strong, so take this with a grain of salt. Locality is very, very important, and we need to build caches for sure. Even if you're doing in-memory computation, you do need those caches. But maybe we don't need 200 different papers on DRAM caches. I see all of these really, really incremental papers, and some really forward-looking ideas are sacrificed because these really well-understood concepts, people empathize with them much more easily. Right? I think this will be another pointer to structure of scientific revolutions. You have a paradigm, business as usual, caching. Oh, it fits my paradigm, accept. It fits my paradigm, accept. Business as usual. Oh, DRAM cache, that sounds interesting, accept, right? A completely different thing that comes to your paradigm and says, oh, you get rid of caches completely and do something else. It doesn't fit my paradigm, reject. That's the structure of scientific revolutions explained in 1 minute. Okay, let's switch gears a little bit. Let's not talk about caching a lot more. let's talk about other opportunities with emerging memory technologies. I'm going to cover the first one. I think merging of memory and storage is really, really interesting. This is actually not a new idea. Single-level stores were examined in the past. Atlas Computer had single-level store, single interface to both persistent and volatile data. IBM AS400, actually, there's a beautiful paper, beautiful book on IBM AS400 by Frank Soltis, who was a chief engineer at IBM, that essentially talks about merging of memory and storage in IBM AS400 and how they did that. And the motivations are very similar, except the technology is very different. Basically, they didn't have a technology that was very close to DRAM in terms of persistence. But now we have a technology that's very close to DRAM in terms of latency. Now we have a persistent memory technology that's very close to DRAM in terms of many characteristics. So can we enable this? This could also, of course, enable new applications. Very fast checkpoint restore is one example. Fast boot up is another example. Sure. If you can come up with better applications, that's always good. It could lead to more robust system design. You can reduce data loss. That's also good. And I'm not going to talk about this, but I've alluded to it, and there's work going on at Technion on this, basically. I think emerging memory technologies can be very good substrates for processing that's tightly coupled with memory, inside memory. Memristors are an example. There's also works on phase change memory that looks at that, SRAM. I think those are very, very interesting, but I'm not going to cover this. But I'm going to cover this one over here because that's also very, very interesting. So basically, if you look at modern systems, we have a two-level storage model. DRAM is volatile, and it's directly exposed to the programming language through loads and stores. And the second level of storage is really persistent. And you access it with a completely different interface, right, with file I/O. And this has evolved because of technology discrepancies. Basically, this technology was extremely slow and non-volatile. This technology was much, much faster, and it was volatile. As a result, persistent data got stored over here, and it got accessed with block addresses. Yet DRAM was fast and volatile, and it was byte addressable over here. Now, if you have non-volatile memory, it sits somewhere in between. Basically, it buys you non-volatility. It's not slow, it's fast, and it's byte addressable. Basically, it combines the benefit of both memory and storage as we traditionally think about them. So can we actually get rid of this disparity in the storage model and make it single level? So that's another picture, actually. The traditional two-level storage model actually becomes a bottleneck with non-volatile memory. So what is that? You have volatile data in main memory, and you have a load-store interface. And that interface today is very heavily accelerated because this device is extremely fast, DRAM. So people have put a lot of effort into the virtual memory subsystem, address translation subsystem, to make it extremely fast, right? This is on the order of nanoseconds to get to main memory because this is on the order of nanoseconds, right? On the other hand, persistent data is in this very slow technology, and traditionally it's been extremely slow, right, on the order of milliseconds with hard disks. And as a result, we access this through some completely different interface, the file system interface. And this, we could afford this to be very slow. The software interfaces are actually very slow over here. To open a file, you go through many, many system calls. And actually, once you open the file, you buffer it over here so that you can operate on it fast, and then you put it back over here. OK. So the key issue is if you actually replace this very slow technology with a very fast technology that's persistent, like phase change memory or STT-MRAM, now this actually becomes a big bottleneck. The operating system and file system code to locate, translate, and buffer data in memory become performance and energy bottlenecks with these fast non-volatile memory stores. So wouldn't it be nice, actually, if we change the paradigm a little bit and go back to the single-level stores that people have examined in the past with this new technology? So our goal is to actually unify this memory and storage management in a single unit to eliminate all of that wasted work to locate, transfer, and translate data. Because all of this work over here in the operating system and the file system is done to locate, translate, and buffer data into DRAM so that you can operate on it and you can write it back in a reliable manner. OK, so the idea is very simple. You have a single interface, load-store interface, to all of your data. You could treat it as persistent or not persistent. doesn't matter, but we'll call it the persistent memory manager because it enables the manipulation of that persistent data. This improves, hopefully, both energy and performance, as we will discuss, and it also, in my opinion, simplifies the programming model, at least over time. So let's take a look at it. Basically, this is what we would like to do. It provides an opportunity to manipulate persistent data directly. And what's the idea? This is one potential programming model. It's not a new programming model. It's old. People have proposed persistent objects. Basically, directly expose persistence to your programming language. Right? Your programming language, you open a file or whatever. This array is persistent now. And you update it. And that update directly gets reflected in your persistent memory. And if for some reason you turn off your computer and turn it on, you can continue from this program at that point. That's what we would like, ideally, right? This way, you don't need to really go through something to open the file. So basically, we'd like to be able to do all of this with loads and stores, and we'd like to provide hints from the OS, software OS and runtime. And we have the software-hardware cooperative persistent memory manager that manages a lot of things internally. Underneath, this could be very heterogeneous, right? Underneath, yeah, this doesn't have to be only NVM. To accelerate things, you may have DRAM. And to have even higher capacity, you may actually have hard disks, SSDs. So underneath, this could be very, very heterogeneous. And the management is up to this persistent memory manager. So the key question is, can we enable something like this? But this thing can be enabled because you have this technology. You could also try to do it without this. And that's essentially what I just described, the IBM folks tried to do with hard disk technology. It may be possible, but the problem is this is very slow now, right? Here, NVM is very fast. So this persistent memory manager uses access and hint information to allocate, locate, migrate, and access data in this heterogeneous array of devices. That's a bunch of words over here. So what does it do? Basically, it exposes a load store interface to access persistent data. Applications can directly access persistent memory. There's no conversion, translation, or location overhead for persistent data. You don't move it from the disk to DRAM and then adjust all of those mappings to be able to locate your data and then move it back and to ensure persistence, right? It manages data placement, location, persistence, and security. That's a lot over here. We don't know exactly how to do all of that, at least at the very fast latencies, right? The latency now needs to be very fast over here. Okay. And it manages metadata storage and retrieval. Basically, you need to keep track of metadata, usually, and this leads to overheads that can be managed. So you need to have something like a page table, I think. And it exposes hooks and interface for the system software to enable better data placement and management decisions. So there's a lot here that I'm not going to really cover. And we have this position paper that evaluates some of this. So I'm going to give you some examples of this position paper. So basically, a persistent memory exposes a large persistent address space, but it may actually use many different devices to satisfy the goal, as we've discussed over here. I think the key enabler is really these fast NVM devices. And performance and energy can benefit from good placement of data across these devices. You want to, again, you want to be heterogeneous and exploit that heterogeneity. So let's take a look at two important characteristics, locality and persistence. There are other characteristics also, but you may have less locality or more locality, and the data may be temporary, or you may need persistence requirements. So one example could be columns in a column store that are frequently scanned. It's scanned through only infrequently. You don't have a lot of locality over here, but you need persistence. So maybe putting it into Flash is good. I don't know. Or you have a frequently updated index for a CDN, content delivery network, that is temporary, and you don't need to be persistent because you can actually always refresh it somehow. But you may have very good locality and you place it over here. So if you can characterize your data, you can actually provide these hints for data placement into this persistent memory manager. And internally, you can actually use those hints. So basically, what we've done is we don't even use these hints, actually. We wanted to evaluate different baselines and how do they perform if you actually manage them with the two-level storage model versus the single-level model that I've kind of alluded to, although I didn't really go into the details of it a lot. So basically, I'm going to show you evaluations with some applications with different baselines. This is basically a traditional hard disk. Unfortunately, we don't have SSD results over here. We should have. We should have evaluated that also. But it's going to be in between hard disk and NVM baselines. So basically, this is a traditional system with volatile DRAM memory and persistent hard disk. We model the overheads of operating system and file system code and buffering to access persistent data. So this is a file system interface to access the data that's in hard disk. And if you're accessing volatile data, you go through DRAM as normally. This is basically the traditional system that we have. The second one is non-volatile memory baseline. This is exactly the same as this, but you replace hard disk drive with NVM. And you manage it still with the existing operating system and file system code. So it still has the overheads of this two-level storage model. And the third one is we get rid of DRAM in the system, and we replace it with NVM completely, and to ensure full system persistence, at least in main memory. All data is accessed using loads and stores, and it doesn't waste time on system calls, basically. And data is manipulated directly on the non-volatile memory device, in this case. So those are a lot of upsides over here. Yes?
If you use, in a conventional system, memory map files, so that you open the file, pay the overhead once. But once it's open, it's actually mapped.
Mm-hmm.
And then it's a load store, of course, depends on which medium you're using. But
Exactly.
load store. Which of those options, if any, would represent that?
So we actually do that. We use the memory mapped thing. So exactly, yeah. Yeah, but the overhead is still, if you're doing a lot of manipulation on persistent data, yeah. So we're assuming a state-of-the-art system with memory mapping. But even that includes overheads, right? And some of the applications we evaluate are actually doing a lot of persistent data manipulation. Okay, so this is what we get. I don't remember which application it was, but you can read the paper for that. Basically, this is an application that's very I/O intensive. It opens a lot of files. It does a lot of manipulation, quick manipulation on the files. And this is the execution time on a hard disk-based system. This is two-level storage. As you can see, most of the time is actually spent on hard disk access. If you actually replace the hard disk with non-volatile memory, remember there's DRAM here, there's DRAM here. If you actually replace the hard disk with something like phase change memory, that's 4x lower than DRAM, I think, in these evaluations. You get 24x performance improvement, which is not bad. But it's not fair because SSDs buy you somewhere over here, probably. We don't know, maybe somewhere over here, actually. But still, this makes sense. You have a much faster medium to access persistent data. But your now bottleneck shifts. Bottleneck is actually really system calls. You spend most of your time, even though that looks little, most of your time is actually spent on the system calls to manipulate, to basically access persistent data. Now, if you get rid of DRAM from here and keep the PCM and get rid of the two-level model, get rid of the system calls, and do loads and stores, of course, you need to rewrite your application to be able to do that. Now, this is what you get. Basically, it's about 5x more performance improvement. And we got rid of the DRAM in the system, so this is hopefully a less costly system. But if you actually add back DRAM, you gain even more performance, as I may show you in another work if you have time. So that's the idea. Basically, this is the benefit that you get by going into a single-level store. Even if you eliminate the fast technology from your system, you get a lot because you can directly access your persistent data. That's the idea, without going through the system calls. And this is the energy. It has very similar trends. This is the hard disk-based system. You get about 16x improvement in energy if you actually replace the hard disk with something like phase change memory. And now your bottleneck is system calls again, although that's not as clear because it's a bit harder to account for that. But you get basically 5x energy reduction if you get rid of DRAM and you change your interface such that you're accessing persistent data with loads and stores. And the paper has a lot more detail, actually. Actually, this was the paper that I presented this was my first visit to Israel in 2013 with, when Weed was with ISCA at that time. Yes? Yes, yes. We're not getting rid of virtual memory. Basically, we're just getting rid of the system call overhead. And the paper actually analyzes like how you get rid of that system call overhead, because you add some more overhead in terms of Because you need to have some sort of overhead, right, to manage the file. It's not magic. You cannot just get rid of the file system without adding some more overhead. So there's some overhead that's accounted for in the paper. If that overhead becomes too much, then that it starts eating into your benefit significantly. Okay, yes?
Do these graphs take into account the problems with the load and store in the new technologies, or they're just like on a theoretical same load and store performance?
What do you mean problems with load and store? The latency?
For example, in
Yes.
PCM.
Yes. So this assumes that phase change memory latency is 4x slower than DRAM.
And in the same capacity as well.
In the same capacity, yes. Yes, we're not adding more capacity here. Yeah, all of our evaluations assume the same capacity. Yeah. So the capacity of PCM over here is the same as the same capacity of PCM over here, except there's no DRAM here. So this actually system is a little bit crippled because the fast technology goes away, whereas this system is DRAM, NVM, but NVM is part of storage model. Yes?
So another possible way to eliminate system calls would be to use something like heuristics IO, like SDK, but still with the NVMe technology and not with the persistent memory.
Mm-hmm.
So do you think it would be much worse than what you got, or how did you compare them?
So basically, you have a much leaner file system. That's what you're thinking of?
Yeah, or even assign the complete NVM device to the application directly.
Oh, I see. So how would you access the NVM device in that case? You don't use the system calls, but you directly access it, loads and stores. Mm-hmm. But you don't have the file concept anymore.
No.
Okay.
Or you have it as part of the application, as a library operating system.
Okay. And there's no conversion overheads. I think if you get rid of the conversion overhead somehow, you could take advantage of similar benefits. Yeah. But I don't know. It needs to be evaluated, of course, right? We didn't evaluate those things. And of course, there's a lot of inefficiencies in the file system and operating system code. You may actually make it a lot leaner and get closer to these benefits. Okay. Any other questions? Okay. Okay, I think this is a big challenge and opportunity also, combining memory and storage and a unified interface to all data. I think this is probably a good place to take a break, and then we'll talk about some consistency issues very quickly, and then we'll move into the new topic. So how about we come back at 15:40?